Okay, so let's pick up from where we left off last lecture. Okay, so yeah, we left off here. So deep Q learning. So previously, we just assumed we could enumerate all possible combination of state and actions. But realistically, especially the states, if you have continuous state space or that it's ginormous, like images, then it's practically impossible to store everything in the memory. So what do? So that's where we introduce function approximators. Doesn't have to be neural network. So it could be some linear model. It could be as simple as, I don't know, S transpose phi or something like this. Okay, doesn't have to be neural network. Anyways, since this is the intro to deep learning class, we're going to use neural network. And because neural networks are especially good when it comes to generalization across similar states. So for similar states, we want the Q output to be similar. Okay, so in terms of the architecture for the Q network, it's going to take in high dimensional state S. And typically the actions are going to be discrete, for example, for playing computer games or things like this. Doesn't have to be. But if you have small number of actions, then implementation-wise, you might as well just push only the image state as input and make it output Q values for that state for all actions. And you'd act greedily according to Q. So take the one with the highest QSA combo. So it's basically same as Q learning, but with deep learning as the Q approximator. So if you remember, tabular Q learning, you had the regression target, which is the immediate reward plus discount times one step greedy Q value for the next action, next state. And in DQN, what you do specifically is you create a copy of the network. And this copy, let's call it phi negative sign. This is a snapshot of the network, because in terms of the optimization, if you backpropagate both the target and your variable, then it can lead to numerical instability. So you just freeze the target and do regression towards that target, and only occasionally update your snapshot. So periodically, this is synced to the current value of phi for stability. So what exactly is the loss? Given the transition, state, action, reward, next state, you compute the target based off of some previous snapshot. And you simply minimize the MSE error between the target and your current Q value for that specific state action. So notice the parameter difference. We're going to do backprop with respect to phi, but this is frozen. So no backprop here. Okay. All right, so another thing besides this frozen target is experience replay. So in DQN, they store past transitions in a replay buffer. So for training, you sample mini batches uniformly from the replay buffer. Okay, so you have agent, execute some action according to the current policy to the environment. Environment gives you state action reward next state. It gets inserted to the replay buffer, and then you're going to sample a mini batch from the replay buffer. And you're going to apply stochastic mini batch gradient descent. So this immediate transitions don't get used during training. They get inserted into the buffer. It might pop out locally, but chances are very low. So it's known that having this replay buffer breaks the correlation between consecutive samples, because otherwise you'd be using this guy and ST plus 1, AT plus 1, RT, ST plus 2, and so on, because the environment is going to continue. So you'd be updating, if you update based on these temporal segments, then these samples are going to be highly correlated. So turns out breaking this correlation really helps the stability of the algorithm. Plus, you can reuse past experience because this is sample without replacement. So what's the full algorithm? You initialize Q phi and target network Q phi negative sign and initialize an empty replay buffer. And this is your main loop. You choose an action according to epsilon greedy policy. With epsilon, probability epsilon, you perform random action for exploration. Otherwise, you act greedily according to your phi. And then, once you commit on which action to execute to the environment, from current state, you execute that action, and the environment is going to give you some reward and next state, and it gets stored in the replay buffer. And you're going to sample a mini batch of experiences from the replay buffer, and you're going to compute the target, but based off of the frozen target. And you're going to do gradient descent on the phi parameter. And you're going to only periodically copy the current up-to-date phi to your frozen target. So you can apply this for playing Atari games or anything that has high state space, high dimensional state space. So here the objective is to complete the game with highest score. Some of the games are never ending. Some of the games are ending. So the input are the raw pixels from the game state. And actions are game controls like move left, right, up, down, fire missile, things like this. And the reward is whatever the emulator gives you. So I don't know if it's okay. So to make it actually work in practice, you remember the Markov property of the state. So probability of st plus 1 given st should equal probability of st plus 1 given st and some all past history. So if you just plug in the current state image, this is gonna violate the Markov property for lots of environments. So what's done in practice is you stack the image at time step t, and channel-wise stack in decrements of 4. You stack about 4 frames. And that's going to be definition of your state. So the velocity information and things like this is available. So here's the simplest algorithm. Here. No replay. And just simple Q-learning and not having separate target network. So for these games, the numbers are the rewards, and you can see the numbers are really low. But as you add these hacks together, fixed Q, meaning we have frozen target, it improves the reward that you've gotten. And if you use just Q-learning, not frozen target, but use replay buffer, you get huge benefit. And if you combine the two, you get even more benefit. Okay, so this is an example of the stability issues in deep Q-learning. Let me see how many slides I have left here. So I'm going to skip some of the slides because we are behind the schedule. So one of the well-known issue is the deadly triad problem. So if you combine these three ingredients together, then you can come up with a thought experiment where it fails miserably. So number one, bootstrapping. So you're using an estimated value inside the target, the estimated value. And off-policy learning, so data coming from older or like exploratory policy. So using epsilon greedy and using replay buffer. And number three, using function approximation as opposed to Q-table. So if you combine all these together, you have what's called a deadly triad. So combination of these can cause divergence, meaning Q values, if you keep applying gradient descent, can converge to infinity. So I prepared numerical example, so you guys can look at it on your own. It's very self-explanatory. Another problem is the overestimation bias. So inside the target, there's a maximum here. And if you have noisy Q estimates, let's say our target is some ground truth plus some zero mean noise that depends on the action. Then if you select the maximum for that action given a state, then it can be greater than, on average, it can be greater than the maximum selected from the ground truth because of the noise. So your max operator inside the target can overestimate the Q values. So the way it's set up, it can systematically overestimate the target value. So that's another well-known problem. So what's the workaround? So I'm not saying this solves all the problems. So this is a proposed approach that partially addresses the problem, but this is not the solution. It just helps us a little bit. So this is called double Q-learning. So if you compare the standard Q-learning target, you have a max of next action from the frozen network, which is equivalent to selecting A star, the argmax among the actions, and plugging in A star here. Exactly identical. So if you notice, we're using the same network used for two roles. One is selecting the argmax action, and one is evaluating the selected action. So if one action have accidentally overestimated the Q, then max selects it with the noise added in and uses the same overestimated value in the target. And it can just, the Q value can fit to the overestimated value and it can just blow up to infinity. So the idea in double Q learning is to separate the two roles, action selection and value evaluation. So for selecting the max target action, you're going to use the original network, the up-to-date network. You're going to plug that in, and to evaluate the Q value for A star, you're going to use a frozen target. So the idea is online network selects the action while the target network evaluates the action. So this is one way to mitigate overestimation bias. But like I said, the disclaimer, this doesn't solve everything. It may or may not work. Another approach would be to use multi-step returns. So when we talked about Monte Carlo-based TD0, I also said you can use multi-step returns, TD lambda or TD1, TD2, etc. So right now our one-step target is immediate reward, discount times estimated next state Q value. And multi-step target is just to look at n-step look ahead or n-step discount sum of rewards, so immediate reward, discounted next step reward, etc. for n steps. And onwards, you use max up K, so max up the Q, or the expected reward starting from the step n step forward. So you could use this for the Q learning target. It's known to reduce bias from the bootstrapped estimates. And in practice, if you could do this, sometimes you cannot, but sometimes if you can, then it helps reduce bias. But you cannot always do this, especially if you use replay buffer. It's hard to implement it this way because replay buffer is just some Q with immediate transitions. I don't know, maybe if you use some smart data structure, maybe it's possible. But if you use just simple Q, then it's going to be difficult to implement this. So what's the summary? We talked about the main theme of lecture 23 was two things: model-free RL. We talked about Monte Carlo versus TD learning. We talked about SARSA, Q learning, and epsilon greedy for exploration versus exploitation, and talked about DQN and deadly triad, Q overestimation bias, and double Q learning, and multi-step rewards. All right, so hopefully we're going to be able to finish RL today because I want to cover quantization, KB cache compression, and more modern methods. The slides are long, 56, and I'm not going to have time to cover everything. But I think the derivations are quite explanatory. So if I skip some of the proofs, you can read it on your own and study. And this may or may not come up in final. Everything's a fair game if it's in the slides. Okay, so yeah, last time, which was partially today, talked about model-free learning, TD learning, Q learning, DQN, and today's focus is policy gradient method and actor critic. And when I made the slides, I became ambitious and wanted to cover the most up-to-date stuff, which is PPO and GRPO, which is used for fine-tuning LLMs. And unfortunately, that means we're going to have to cover less of the actor critic. So what's policy gradient method? So what's the goal of RL? It's not the Q, it's the pi. If you have the policy, you're done. So value-based, you want to learn Q, and you want to extract the policy from the Q. But what if you could learn this directly? That would be ideal. So previously in value-based methods, we chose actions by first learning the Q and extracting the policy by querying what's best action for a given state. And for continuous actions, solving this optimization over actions may be difficult because Q may be non-convex, and this can be another difficult optimization problem. There's a way around this. We can talk about it in actor critic if we have time. But what we want to do is we want to learn this, optimize for this directly. And how do we parameterize this policy? So for discrete actions, we're going to apply softmax of some function, neural network function that takes as input a state. And this is going to output a real vector in how many actions there are. And for continuous actions, we can make an output a Gaussian policy. So the network outputs the mean parameter and covariance parameter that all depend on the state. And it's going to output a distribution, Gaussian distribution on the next action. Then we can sample from this Gaussian. Anyways, okay, so what's the objective, right? So let's just think purely in terms of optimization and forget about RL for now. What do we want to optimize, and let's just go for it, right? Okay, so it's expectation under the trajectory that's influenced by the policy of the return of the trajectory. What is a return? It's discounted sum of rewards. What is a trajectory? Starting from some initial state, D0. Some papers use rho. Action, next state, etc. So we already talked about, we defined this already in the first RL lecture. What is how do we define the probability of a trajectory? It's just a probability chain rule. Initial state is sampled from initial state distribution. Then we execute an action according to the policy distribution. And given the state and the sampled action, environment distribution tells us the distribution over next state. And just goes on and on. Here, the important observation is we want to formulate an optimization problem in terms of the data, the parameter for the policy. And the important observation is only the policy depends on data. So if you formulate the optimization problem and hit it with a gradient, hopefully everything else will disappear except the policy. So the observation is initial state distribution, environment distribution doesn't depend on data. So suppose the sample trajectory gets high in return, then the action taken in that along that trajectory should become more likely. So this is the intuition. So the intuition of policy gradient is for each trajectory, you want to increase this guy, which is gradient of the log of the policy value weighted by the trajectory return. So let's say you have your initial state as 0, sampled, deterministic, and you execute a sequence of actions. These are the actions. I'm just going to draw the actions only. And then you get the final return of +10. On an alternate universe, you execute A1, A2, etc., and you get -5. And for another action sequences, you get +7, etc. So the intuition is you're going to weight by the return of the trajectory. And if it resulted in a high return, you want to increase the likelihood for the specific action policies. And if it was really bad, we want to decrease the log probability of these actions and moderately increase something in the middle. So we want to increase the probability. We want it to be more probable that these actions are taken if they landed in high return. Once again, ChatGPT switched the order, and I personally don't like this. I like to start from here and derive it, but this is the end result and what it means. Okay, how do we get there? Comes here, okay. All right, so let's look at very simple lemmas. So for any differentiable probability function p theta, if you compute the gradient, it's equal to p of x, gradient log of px. Why? Because gradient of the log of px is gradient of the px divided by px. Multiply both sides by px. It gives you this trick. So gradient of this differentiable probability p theta of x is itself gradient log px. Okay, so how do we compute gradient log of probability of trajectory? Sum of all time steps, gradient log action probabilities. So initial state and environment dynamics all vanished from in the equation. Why? Let's just copy paste the probability distribution for our trajectory. Take the log and hit it with the gradient. These guys go to 0. It's obvious, right? Okay, so let's use these lemmas and derive reinforce. So our ultimate objective is expected return following this policy. Okay, so let's just rewrite the expectation with the sum. I'm going to differentiate it with theta. Then this guy from the log derivative trick here, I'm going to replace it with p of tau, gradient log of p tau. Right? Therefore, I'm going to also now rewrite this in terms of expectation. So we have expectation of the trajectory of gradient log probability of the trajectory, return of the trajectory. And we're going to use this lemma. Gradient log trajectory probability is sum of time steps, gradient log action probabilities. Okay, let's insert that from here. Okay, I'm going to just replace it with this guy. Right? So insert that. Now we have reinforce. Okay, gradient of our objective is expectation of the trajectory, sum of all the time steps, gradient log action probability weighted by the trajectory return. So this is basic policy gradient or reinforced algorithm. There's one issue here though. So mathematically everything is correct. But if you think about it logically, something doesn't sound correct. So for action AT, rewards that happen before this time step T cannot affect this action. So those past rewards, they contribute 0 in expectation, but add noise to the sample gradient. Right? So just look at it in terms of some time, and let's say we're going to execute some action AT. But whatever rewards we had here, these rewards R1, R2, R3, R4, R5 cannot have been influenced by action AT. Right? Unless this guy time traveled through some time machine and did something, right? So logically, something doesn't seem right. But mathematically, everything's correct. So these interactions are only going to add noise, and this is going to have a very high variance if you implement it as is. Okay, so that's where reward to go comes in. So let's look at another lemma. So expectation under an action of gradient log action probability is 0. So RL people call this EGLP lemma, expected gradient log probability. So let's write this in terms of sum of, let's unpack this expectation. And this guy, differentiable policy, gradient log policy, that's log derivative trick. So that's gradient of the differentiable probability by theta. Let's take this outside the sum, and that's 0. So expectation of action of gradient log action probability is 0. So for some specific action AT, let's consider the policy gradient term. And let's define the history before that action AT as HT. So starting from state 0, action, reward, blah, 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 until the state ST. Let's call this guy HT. And for any past reward RK, already determined by HT, and for any passive word RK, I'm going to look at this expectation. So expectation of gradient log action probability weighted by this reward RK, which is fixed if you condition on H. So by tower property, so just to make it explicit, this first expectation is over random variable HT. And if you condition on HT, RK is fixed. So inside the conditional expectation, this can move outside because it's fixed given HT. So let's take this outside the inner expectation. But given HT, the randomness is the action. Okay, so let's unpack this a little bit. So inner expectation is, I'm just going to rewrite the expectation. So sum of A weighted by the distribution of the action, gradient log probability, and that's by the EGLP lemma 0. So expectation of gradient log action probability weighted by some reward that happened before this action is all 0. So the takeaway is passive words are zero mean noise for the gradient at time step t. So future rewards may depend on action AT, so they must remain. So at point t, time step t, action AT has no influence over the previous rewards, but has influence over the future rewards. So these guys can move outside the expectation, but not these guys. So here comes another definition, reward to go policy gradient. Reward to go is starting from time step t, sum of discounted future rewards. So policy gradient can be written as expectation of the trajectory of sum of time steps, gradient log action probability, weighted not by the entire trajectory return, but only weighted by return to go. So action AT is reinforced only by rewards received from time t onwards. So this is the reinforced algorithm. And this still can have high variance. So additionally, what you can do is add a baseline. So if we subtract a function that's only a function of state, this doesn't change the expected gradient. Because for any function b that only depends on state, we can move it outside the expectation by the same logic. You can derive it on your own. So just use the tower property again and same conclusion. Under the expectation, you can add or subtract or anything you want. It's not going to change the expectation as long as it's a function of state. So what is the common form of baseline? It's to use the value function. So return to go minus the value of a state measures whether the observed return was better or worse than expected. So this is the expected return starting at state st, executing the policy pi. And this is what you actually got. So it just tells you whether it was better or worse than expected. So this is called the advantage estimate. So the policy gradient now is expectation, sum of time steps, gradient log action probability, weighted by the advantage. So if this action had positive advantage, you increase the action probability. If it was negative advantage, you decrease action probability. So without this sort of mean subtraction, then what if all your returns were positive? Then you will end up reinforcing everything, although they are weighted. But with this, then even though you have all positive returns, this mean subtraction will actually decrease some of the actions that's below average. So this was advantage estimate. And what is the true advantage? True advantage is, as opposed to using return to go, you use the Q value. So policy gradient with true advantage is here you weight by Q minus V. So to implement this, you will need 3 networks. 1 neural network for this, 1 for this, and 1 for this. To implement this guy, you're going to need 2 neural networks, 1 for the pi, 1 for the V. Okay, so okay, let's move on to PPO. So PPO is another policy gradient algorithm, which is very famous because most RL algorithms are very unstable, but PPO is I think what most people use as a first trial because it's so reliable. And so let's start from looking at our policy gradient. So the idea makes sense. So with positive advantage, you want to increase the probability of action. And with negative advantage, you want to decrease the probability of action. Makes sense. But the problem is, if you update your policy too much, it can destabilize the training. So what we would like to do in addition is we don't want it to deviate too much from the old policy. Because advantage collected under the old policy may be no longer reliable. So we want to control the update size by comparing the new policy to the old policy. So from this policy gradient for a fixed batch of sample trajectories, this is the gradient of the local objective. What is the local objective? It's expectation gradient, expectation sum of t log action probability weighted by advantage. But these sample trajectories were collected by the old policy, and we want to update the new policy pi data from it. So let's look at it from the importance sampling point of view. So we're sampling data from pi old, and we want to update it to pi new. So suppose we want to estimate expectation under distribution P. In case you've never seen importance sampling, but our sample comes from another distribution Q, the old distribution. So expectation of some function under P distribution divided multiplied by same distribution Q is actually expectation under Q distribution of importance sampling ratio that adjust for this. So the interpretation is if sample come from Q, we want an expectation under P. The correction factor is we want to weight each sample by how much more likely it's under P than under Q. So what we're doing, basically data is collected by the old policy, pi theta old, but we want to evaluate the new policy under pi theta. So the importance sampling identity from previous slide, P, that we would like to sample but cannot, is pi theta. Q, what we ended up sampling instead was pi old. So the importance ratio here is pi theta over pi theta old. So the natural policy improvement surrogate is same thing, but weighted by this importance ratio. So if this ratio is greater than 1, policy assigns higher probability to the action. If it's less than 1, assigns lower probability to action. Yeah, I'm going to skip this slide, but you guys read it over. All right, so what's the objective? So previously, without importance sampling, we had expectation, sum of t, log of action probability, weighted by advantage. Now we have this importance sampling factor in front to compensate that. And in addition, this policy importance sampling ratio can be very flaky in place because we have probability divided by probability. So what it does to make it work is to introduce this clipping. So it's going to take minimum of the two. This is without any clipping, and this is with the clipping. So you're going to take this importance ratio, which is distribution over distribution, and clip it with the lower bound 1 minus epsilon, upper bound 1 plus epsilon. And then you're going to multiply the advantage. So always, if you have probability divided by probability, you can expect it to not work in practice. You are always going to have numerical issues. So what they done in PPO is to introduce its clipping. So this probability ratio, the lower bound is going to be clipped. If it's less than 1 minus epsilon, it's going to get clipped to 1 minus epsilon. If it's greater than 1 plus epsilon, you're going to fix it to 1 plus epsilon. So the interpretation is, okay, it's good to have this calibration factor coming from the importance sampling ratio, but in practice, we're going to clip it so it's numerically stable. So it keeps the policy update close to the update policy while still following the advantage-weighted policy gradient direction. So the idea is you want to prevent overly aggressive policy updates. So for example, let's say we're driving up a mountain and the car is going straight. And here you have a seaside. And if you make too much aggressive of an update, and you're going to jump straight to the seaside, and you're never going to observe any data past that point. So you're going to make your update more conservative by introducing this clipping ratio. So why am I talking about this all of a sudden? And how is it connected to LLMs? So for language models, how do we define a trajectory? It's basically a generated sequence of tokens given some prompt. So the policy is a language model given some prompt and past tokens. You want to output a probability of next token. So probability of completion is just a chain rule multiplying autoaggressively all these action probabilities. So action each step is the next token, and reward can come from multiple factors. So one is human preference, and sometimes you have verifiable answer correctness. Sometimes you have rule-based reward and safety or formatting reward. So I don't think I have supervised point. Okay, so let me explain what these mean. So first of all, human preference reward model. So sometimes if you use ChatGPT or any generative model, in the UI, you make some prompt, and ChatGPT gives you two options. Option A, option B, which do you prefer? And you click one, right? So what you click becomes a supervised, it becomes a label for human preference. So during development, the developers have made it so that it outputs a number of different responses and have humans annotate or rank different items based on their preference. And what they've done is they trained the supervised model to predict the human behavior because humans are not scalable. So that they learn a separate neural network that can mimic human labels. And based on that, you have this black box function that gives you reward. Same thing for safety. You might have human labelers label each output and flag inappropriate answers that include curse words or explicit content or things like this. And then upon procuring enough samples, you can train a black box neural network that outputs a number proportional to the safety of the output. So these black box neural network models can serve as a reward function. So what's the context? Why can't we just do supervised learning? If you do just token generation, then you're stuck to this perplexity or likelihood. How likely is it based on our data, right? But if you want to do more complicated things, like incorporate human preference, measure safety, you need to work with the black box function that gives you some number. This may or may not be differentiable even. That's where RL comes in. You're going to treat these different models as some reward that environment gives you, and you're going to initialize your model from the supervised fine-tuned model based on likelihood or perplexity, and then you're going to fine-tune it based on these complicated rewards that mimic human labeling behavior. These are really hard to write down mathematically, right? So you can only model them using black box neural network. How do you mathematically write down how humans label safety of a response? Or how do you mathematically write down how humans think response A is more appropriate than response B? It's impossible. That's why we collect lots of human label samples, train a black box neural network that mimic human labelers, use it as a reward, treat it as complicated black box, and use reinforcement learning to fine-tune our LLMs. So our policy gradient objective is to maximize the sum of the rewards, but with one regularizer. We want to penalize the KL divergence of the policy output from deviating too much from this supervised learning pre-trained model. So this KL penalty is just to safeguard us from RL just offshooting to something completely different. But important thing is this part. This reward function is very, very complicated, and we cannot mathematically specify what it is. So we learn some black box model, and we're going to use RL to maximize this. Not very important. Okay, so what's the objective? So for a generated completion, we introduce this correction factor coming from importance sampling and use clipping, just a plain old PPO objective. That's what we want to optimize. But at the same time, we're going to enforce this so it doesn't deviate too much from the supervised fine-tuned model. So one issue for PPO, for extremely large language model, is you need to keep around the value model. This is another neural network. So we want to train, ideally, we want to train as large model as possible, right? We want to download the entire internet and train an extremely big model. But if we have to keep around this another big model, then it effectively eats up our GPUs. So how can we do this more efficiently? That's what GRPO introduced. So this came up from the DeepSeek guys. So they just modified it just a little bit. So if you look at the PPO objective, it uses a learned value function v of phi. And you take the actual return to go you obtained and subtract it from this neural network estimate, basically the average expected reward. So the idea is you're going to sample a group of completions and compute the relative advantage within the group. So here's the so idea here is actual return you got minus expected reward that you would expect starting from the state, right? So for a prompt X, you're going to sample a group of G completions. So as opposed to sampling just a single trajectory, you're going to sample multiple trajectory. So let's call them Y1 through YG. And you're going to simply compute the sample mean. So here, we're supposed to just plug in ST and subtract the black box output from neural network. But here, given some prompt X, we're going to generate multiple trajectories. Compute the sample average, subtract it from individual returns, R1, R2, RG, and also we're going to divide it by standard deviation. So interpretation is a completion gets positive advantage if it's better than the completion for the sample for the same prompt. So here, what's nice is you don't need any separate value network. But what's the downside? You need to generate multiple trajectories. So it can be slow because you're going to generate multiple trajectories and compute the sample mean as opposed to a single call to the black box function. But you can save memory and use more GPUs to increase the model size. So what's the GRPO objective? Rest of them is exactly the same. It's just that this definition of advantage estimate is different. This guy. They use identical PPO objective. So they got rid of this value network altogether, replace it with sample mean. That's the idea. Okay, so we discussed PPO, which is probably everybody's first choice because algorithm is so robust. And PPO uses a separate value network. GRPO uses sample returns. And what's the usage? Reinforcement learning with human feedback, control, any RL task. And memory cost is higher for PPO because you need to maintain in the memory in the separate network. Okay, so surprisingly, we have some time left, which is good. So let's try to cover this as fast as possible because I want to finish RL today. So actor critic method learns both the policy network and critic network, or Q or V, or both. So how do you train this extra value critic? You can do MSE loss based on the actual returns, or you can do TD learning. You can learn it against itself from one-step transitions. So how about the actor? Actor is a policy, by the way. Simple. You do policy gradient weighted by the advantage, but inside the advantage, you use these critics. And then you apply gradient descent here. And so you have two choices when you implement the advantage: reward to go minus black box estimate of expected return, or you could do even a TD style update. You have immediate reward plus discounted expected return starting from next state ST plus 1 minus expected return starting from ST. So TD style update. You can do either. And for actor, you're going to do policy gradient. For critic, you can do MSE loss gradient descent based on the actual return. Or you can do TD. So why am I talking about this? So one question is, which we haven't addressed so far, is, okay, what if I have a continuous action? So for example, for robotics, you want to control the amount of torque in each joint. That's all continuous. That's not discrete. So even if you have some Q, maximizing overaction may be very, very hard. For discrete action, it's trivial. You can just insert everything or have Q network output Q values for all actions. For continuous action, this is very, very hard. So the idea is we're going to learn an actor network that approximately returns the maximizing action. So we're going to train a pi that will output the argmax. So here is an algorithm called DDPG. They use deterministic actor, and it's trained to maximize this. So here we're going to apply gradient ascent on the actor parameter in such a way that the Q value evaluated at the policy is as high as possible. So we're going to insert this policy in terms of in the action place in the Q, and we're going to apply gradient ascent so that Q value indexed at pi theta is as high as possible. So by chain rule, the gradient is gradient of the Q evaluated at this specific action recommended by the policy times the gradient of the policy. How about the critic? You have the target critic, target actor, and we're going to do MSE loss minimization. So it updates against one-step TDE loss, but also indexed at the specific action recommended by the target critic, target actor. So you do MSE on TD error. And for updating the actor, you do gradient ascent on action index at the corresponding Q value. So TD3 takes this idea and improves it further. So TD3 algorithm introduces 3 stabilizing modifications. First, they introduce clipped double Q learning. So what we're going to do is we're going to maintain 2 separate Q networks in the memory. And to compute the target, we're going to take the one whichever is more pessimistic. Number 2, we're going to update the actor less frequently than the critic. Because taking argmax of some garbage is not really useful. So you want to focus more on learning the Q better. Also, you want to add some noise to the target action, not just deterministic policy. So these are the ideas introduced by TD3, and clipped double Q learning turned out to be very, very important. It can be a great guard against overestimation bias in Q learning. Maintaining 2 separate networks and listening only to the most pessimistic of the Q. And here you might be wondering why 2, why not 100? So we tried it, and if you increase this number to 100, it works even better. But the downside is you need to keep that in the memory. So overestimation bias is a real issue in RL. And SAC improves it even more, and also have this entropy term on the policy. So entropy is negative expectation of the log of the distribution, and more is closer to the uniform distribution, you get high entropy. If you have point estimate, you have very low entropy. The interpretation is uncertainty about the random variable. We used to have a separate lecture in info theory, but we have to delete everything. SAC introduces this entropy term to encourage exploration, especially in the early stages. You want to have high entropy in the policy distribution. Other than that, the equation is more or less the same. So you have how do you compute the target, immediate reward, discounted expected Q, but you only listen to the more pessimistic of the two. You have the entropy, and each critic minimizes the MSA error against the same target. And how do you maximize the actor? Like I said, you sample action from the actor, insert it into the target queue, and you want to do gradient ascent. So whatever action recommended by the policy has as high Q value as possible. Because during inference time, we don't want to solve this maximization problem over the policy. We want to train the actor so that whenever it recommends something, it has as high Q value as possible. So we don't want to reference Q during inference. We just want to have this policy. Why? Because for continuous action, it's very, very hard to maximize this array. And takes a lot of time too. So there is an environment called Bujoko, which is very simple environment where you can train robots to do things. You have access to the motors in each joints. And I think we're going to do this on homework. So SAC is more or less a robust algorithm. I shouldn't say robust, but I think it's a first choice if you want to do this for continuous actions. So what's the summary? So today we talked about policy gradient methods. So we talked about reinforce, A2C, DDPG, TD3, SAC. Reinforce, there's no critic. And in DDPG, you had the Q. And in TD3, you have two Qs. And you listen to whichever is more pessimistic. And it significantly reduces the overestimation bias and stabilizes the training. So, summary, policy gradient method directly optimizes the policy. And we derive the policy gradient, and the baselines reduced variance without changing the expectation. And advantage, the meaning was for this immediate consequence or immediate reward, how much better or worse is it compared to the expected expected value? If it was better than expectation, we increase the probability. If it was worse than expectation, we decrease the action probability. And actor critic methods learn both the actor and the critic. And especially for continuous control, we want to avoid maximizing over the Q over actions. So during training, we train Q, the pi, so that whatever recommended by a pi has as high Q value as possible. So for continuous control, SAC is a great first choice. And we talked about a lot, but I think this was very good in that we also had a chance to touch base to LLMs. All right, that's it for today's lecture. Thanks.